Halo Case Study. Let's review a real-world application that is vulnerable to template injection. The application we'll review is a content management system, or CMS, called Halo. Halo doesn't currently support English, so we'll run the application with a translation plugin. Halo Translation and Discovery. While SSTI vulnerabilities are not always authenticated, it is very common to find them within an admin section, which lets a more privileged user add or edit templates. This is the case with Halo. For this reason, we'll be attacking Halo as an authenticated user. These credentials could have been discovered via a password dump or an authentication bypass vulnerability. In any case, we'll be using the SSTI vulnerability to escalate from an authenticated user to remote code execution. Before we begin poking around the Halo CMS, we'll need to install Google Translate in the Burp Chromium browser. We'll start with Burp Suite Open and click the Open Browser button on the Proxy tab. Once Chromium opens, we'll navigate to the Google Translate extension page and click Add to Chrome. Once the extension is added, we'll pin it to the toolbar for quicker access. At this point, let's navigate to the home page and attempt to translate it. We can translate an entire page by clicking the Google Translate extension and clicking on Translate this page. If everything worked, the text should have been translated to English. With the home page translated, let's navigate to the admin page, log in, and translate it. Once logged in and translated, we can begin to search for an SSTI vulnerability to exploit. We can find SSTI vulnerabilities in many locations, but as with most vulnerabilities, user input is a great place to start. When we have administrator access within an application, another great target to search for is a template editor, which might be used for user emails, for example, or a theme editor. Conveniently, Halo supports theme editing directly in the UI. Let's navigate to this page and try to discover which type of templating engine we're dealing with. The right sidebar lets us select the theme file we want to edit. The .ftl extension that we find here is often used for FreeMarker templates. Let's select 404.ftl and review its contents. Based on the name, we can assume that this page is loaded when the server responds with a 404 page not found error. One of the parts of the document that sticks out is the use of an expression to output the static variable. Let's use curl to send a request to a non-existent page and read the output to determine how this page might be displayed when rendered. The expression in the template was translated to the static variable. Given the file extension and the style of expression, We can assume that this is using the FreeMarker templating engine. Let's perform some additional tests to verify this. We'll start by using double curly brackets to multiply a number. If we are indeed working with FreeMarker, we can expect that this won't do much since these are not the delimiters that it uses. Let's add this payload to the end of the template. We'll click Save on this document and use curl to review the output. As expected, the value is not rendered. Let's try replacing the double curly brackets with the default FreeMarker delimiter. This time, we expect that the numbers will be multiplied. Next, let's try to change one of the numbers from an integer to a string. If an error is returned, this will confirm that the templating engine is FreeMarker. In some cases, this test might crash the entire application, so we should proceed cautiously. This time, we'll send the request and display the headers with -i so that we can examine the response code. The response indicates that multiplying a string and integer crashed the templating engine. At this point, we are very confident we're working with the FreeMarker templating engine. Halo, exploitation. Now that we've discovered the template injection, let's build a payload that will execute commands on the target. We'll start by reviewing the rudimentary FreeMarker expression to execute a command. This payload will return the current user executing the process. Let's replace the payload to instead display the etc password file, save the template, and use curl to render it. When we render our payload, we find the contents of the etc password file. Excellent! At this point, we can execute any command we want on the system. Craft CMS with Sprout Forms, Case Study. The vulnerability we'll explore in this section arises from the popular Sprout Forms plugin for the Craft CMS. As we'll find, this SSTI is blind, meaning we cannot review the output of the SSTI. However, we have ways of discovering and testing SSTI in blind applications too. Craft CMS with Sprout Forms, Discovery. This is an email template vulnerability, meaning we'll need a way to view the emails that we would receive from the application. We can find an SMTP catcher on port 8025 of the same host as our target. Let's nevertheless attack this application from a black box perspective and start discovery as if we have no information about the target. We'll enumerate the application and find the required information to exploit the target. We can start enumeration by visiting the site to view its contents. The home page is minimal, displaying only a form to get in contact with the administrator. Let's inspect the source of the HTML for any clues about the target. The source gives us 2 clues about the application. First, we find that the application is indeed running Craft CMS based on the value of the CSRF token. Next, we find the use of brackets in the name attribute of the input field, which is a common, although not exclusive, feature of PHP applications. Let's run GoBuster to search for additional endpoints on the target. We'll provide it the common.txt word list from Derb and the URL of the application. By running GoBuster, we discover 3 unique endpoints: admin, index, and logout. However, index and logout point to the home page that we've already reviewed. This leaves admin as the only unique endpoint left that we have not reviewed. Let's navigate to it. Upon visiting admin, we are immediately redirected to login. While we don't have credentials, we do find another confirmation that we are running Craft CMS. With the application enumerated, let's attempt a more active attack. Outside of admin login, the only other user input we've discovered is on the home page. Let's attempt to send a valid message to the administrator. With the message sent, let's open our inbox to check for any type of confirmation. We can find the mailbox at the same URL on port 8025. We confirm we received a message via email. Emails are great targets for SSTI since an email will commonly be comprised of mainly generic contents, but will be tailored to the user using some form of templating engine. This is a PHP application, and a web search for Craft templating shows that the Craft CMS uses Twig, so we can assume that this form would also use Twig as the templating engine. Let's try to introduce a Twig template and observe the response. We'll use a payload that multiplies 2 numbers. When we click Submit, the application responds normally, but when we check our inbox, we find no email. Initially, this seems like a mistake, but if we send the payload again, we observe the same result. This must mean the template injection is causing an error somewhere. We might be dealing with a blind SSTI. In order to know if the template is being executed, let's try to change the payload to something that will produce a response. Since we can't review the output, we'll need some form of out-of-band communication. For example, if we can get the templating engine to return a curl request to us, we can prove that the templating engine is rendering our payload and system commands are being executed. Let's use the reduce filter to execute the system command. We'll pass a curl command to our Kali IP. Before we send this payload, we'll start a Python HTTP server to catch the responses. This time, when we send the contact page with our payload, we should log a GET request on our Python HTTP server. Excellent! We now have command execution on the target. Unfortunately, without the response, the command execution won't be very useful. However, we can create a payload that executes a command and exfiltrates the data back to us. Craft CMS with Sprout Forms. Exploitation. Let's use the Twig template sandbox to develop the payload, since we can develop the payload more quickly in an interactive session than via trial and error using a blind SSTI. We'll start the payload with the curl request we already sent, so the command output will be exfiltrated back to our server. Let's modify this payload to concatenate or join some data to the request. Reviewing the Twig documentation, we find that concatenation in Twig is done via the tilde character. Let's name the variable we are concatenating exfil. When we review our Python HTTP server log, we find a request with the exfil parameter. Since we don't have the exfil variable set, its value is empty. Let's work on setting this variable next. We'll have to URL encode any data that we send to ensure that it can be sent accurately. Conveniently for us, Twig provides a URL encoding filter by default. We'll use a statement to set a variable to a string and pass it through the URL encode filter. When we view the HTTP server log, we can find the encoded message. At this point, all that's left is to execute the command we want and replace the message with the output of the command. To execute a command and set the variable, we'll use the set tag to save the entire multi-line output of the command. We'll call this variable output. In the tag, we'll execute the command we want. Let's start with whoami first and later cat out etc password in craft. When we place the template into our sandbox, we will find the output is logged on our HTTP server. With the payload built, let's copy and paste it into the contact form and review the output. This time, however, we'll change the command to display etc password. When we click Submit, we receive a log in our HTTP server with the contents of the etc password file. Let's decode this response in Burp Suite to receive the contents in a readable format. We'll click on the Decoder tab and paste the response into the text box. Next, we'll click the Decode As drop-down and select URL. Once the process completes, we should receive a decoded version of our response. Excellent! We can now execute any command and retrieve the output.
Familiarizing ourselves with the sandbox. Let's browse to the sandbox's main page. This page includes links for PHP, Python, and Node.js command injection, as well as various exercise links. We can use these command injection links to perform injection in a variety of languages. For now, we'll click on Python command injection to walk through a simple command injection example. This page emulates a web application that is running a command. The URL reveals that the IP parameter is set to 127.0.0.1. As the page loads, the output resembles the output from the ping command. Behind the scenes, the page accepts the IP parameter and passes it as input to ping. The server executes the command and presents the output. Since we know that the server is executing a command, let's try to inject our own. We'll safely assume that the command is being run in a system shell. If this is true and the web application doesn't sanitize input, we may be able to use a pipe symbol after the IP value to inject or chain another command, like ID. Here's the altered URL. Let's submit this URL to verify whether or not we obtained code execution. Very nice. We just discovered and executed our first command injection. The system ran our ID command, revealing that we have the ability to execute commands as the www.data user. In the upcoming sections, we'll expand on this technique. About the chaining of commands and system calls. In the case of Linux, we can use the semicolon, the logical and, the logical or, and even a single pipe character. For example, consider a simple ls-ls command run on our Kali Linux VM to list all directories and files in our home directory. As expected, this lists files and directories. As an example of simple command chaining, we will add a semicolon to the end of the command, marking the end of a command in Linux, and follow it with ID. This single-line command executed both commands sequentially. Much more than a simple example, the ID command is extremely helpful as it reveals the user ID we're running as. We can also use whoami, which works natively on both Windows and Linux. We can also use &&& to chain commands. In this case, the second command will only run if the first exits without an error. Next, we'll use the ampersands again and note that if the first command fails, the second one won't run. Alternatively, a logical or double pipe will only run the second command if the first fails. In this example, the second command, ID, did not run because the first command, whoami, exited without error. Let's use the logical or in another example, this time with a command we know will fail. This time, the second command, whoami, runs. Finally, let's discuss some Linux-specific inline execution mechanisms. Consider these examples, which use a backtick character and the null statement to wrap a command. This can be an odd mechanism. Let's create a simple example. Note that the first command is a simple echo statement. However, the second and third command embed "who am I" into the statement. As the name suggests, the embedded command is executed in line, and the command output is effectively merged. Now that we've discussed command chaining, let's turn our focus to typical input normalization techniques that are designed to prevent this type of attack. Typical input normalization: sending clean payloads. Web applications often perform input normalization on user-supplied data, processing it and manipulating it in a way that could adversely affect our command injection payload. Our payload travels a sometimes tricky path before it is processed by the target operating system. It begins in our browser or script, is processed by the target web server, then by the target web app, which often performs normalization and sanitization, and it may be passed to the operating system through a system function where it is executed. Each of these steps will process and may alter our payload and negatively affect the outcome. In the following sections, we'll discuss some techniques we can use to ensure our payload is executed correctly, even as it passes through these various processes. Specifically, we'll discuss bad character replacement, character escapes, URL encoding, and payload wrapping. After achieving system-level command execution, we'll make it a priority to obtain a reverse shell to gain control of our target through a terminal interface. As we begin preparing our payload, we should consider bad characters, which have an assigned meaning along the payload's path. These characters could negate our payload. We can mitigate bad characters by wrapping commands in single apostrophes. The single apostrophes inform the target server that this counts as valid parameter data, rather than interpreting it as a new parameter entirely. Let's demonstrate this with an example. Before we begin, let's set up a Netcat listener to catch a bash reverse shell on port 9090. We'll listen on the 0000 interface, request verbose output, print numerical IP addresses and ports in all output, and bind to port 9090. Let's run our listener with these arguments combined. Now that we have our Netcat listener established, let's consider a sample payload. We've highlighted the bad ampersand characters. These characters would act as delimiters to the back-end web technology. When the payload is sent and processed, the web server will interpret everything after the ampersand as an expected parameter value combination. This would break our payload. To have these characters interpreted in a way that results in code execution will require that we URL encode and normalize the data. To encode our payload, we can use Burp Suite's URL encode key characters feature. We'll load our request into Burp Suite, and inside the Repeater tab, select our payload. Next, we'll right-click and select Convert Selection, then URL, then URL encode key characters. Our payload is now URL encoded and the request is ready to be sent. Encoding is an essential factor in any web payload delivery. To ensure that the target web server, such as Apache or Nginx, correctly interprets various characters and does not invoke truncation or interpret two things as separate statements, we URL encode our payload to ensure successful delivery. Now let's inject our payload into the Node.js command injection sandbox with the curl command. Let's return to our Netcat listener. By sending the wrapped and URL encoded payload, we have received a root privileged reverse shell. Nice. It's extremely important that we normalize our payloads before sending requests. This way, if we encounter problems with our payload, we won't waste time troubleshooting bad characters or URL encoding issues. In the next section, we'll overcome the next hurdle, input sanitization. Typical input sanitization, block-listed strings bypass. Although we've created a simple command injection, this won't work against most targets that sanitize user input. Let's jump in and demonstrate how our typical command injection attempts fail. For example, if we attempt to inject the whoami command at the endpoint, it fails, as indicated by the verbose error message, IP parameter is empty or contains block-listed strings. Let's dig into this a bit more and attempt to alter the potentially block-listed string. For example, we could attempt a null statement injection bypass to break up the string. Let's try this out on our Kali VM. We'll insert a null statement between the H and the O characters in the whoami command. We provided special characters as a statement. Linux then evaluated the statement as null and proceeded to execute whoami. Cool. This is the premise behind block-listed string bypasses. Let's try to run whoami on the web application by visiting the endpoint. After sending our request with the null statement embedded in whoami, our result, www.data, is returned to us at the end of the output. Next, let's improve our approach with wfuzz and a custom word list. We'll use this to check for various combinations of the special characters we've discussed in this topic. We'll keep this word list small so we can carefully examine our wfuzz output, particularly the response length. We want to avoid lengthy word lists and requests that could create errors and generate unnecessary traffic. Let's create the word list and place it in our home directory. Our list includes an additional bogus string, so we can guarantee a failed response length when fuzzing, or at least gain an interesting response, which would render in our browser. This is important because having a known response size when fuzzing a target endpoint is exceptionally useful when we're filtering our results for successful attempts, or verbose error messages at the very least. Now we're ready to launch our automated attack against our target endpoint. As a refresher, this is the endpoint we manually targeted earlier. We'll replace our injected whoami command with the fuzz keyword, which leaves us with this. We'll call wfuzz with a few parameters. The first parameter tells wfuzz that we would like color in our output. The next parameter, -z file, instructs wfuzz to use a file as a payload list input source. We then specify a full absolute path to the word list. Next, we'd like to exclude any not found responses, as they are errors. To do this, we'll provide the --hc parameter with a value of 404. Finally, we have the complete endpoint with the fuzz keyword included. This generates many failed attempts, each with a response length of 1156 bytes. Let's hide these requests by providing wfuzz with the parameter value combination --h1156. Nice. The length of 1113 bytes seems promising. After suppressing a known fail size or bogus response, 1113 bytes seems to be the most common occurrence in our output. We're left with a few that we could attempt separately within our web browser. Let's load the payload from our wfuzz output into our browser and note the response. We have obtained code execution and bypassed the block-listed strings. Before we conclude, let's examine one other possible attack vector to bypass block-listed strings entirely if a backtick character is permitted. We can achieve this with base64 encoding. We'll simply choose the payload we want and echo it into the base64 binary on our attacking Kali Linux VM. Now that we have our base64 encoded payload, we'll begin our injection attempt with a semicolon, and everything after will be wrapped with backticks. We'll pipe this into base64-D, which executes whatever is decoded. Excellent. Our base64 method has effectively mitigated any block-listed string sanitization. In the next section, we'll discuss blind OS command injection. Blind OS command injection bypass. With blind OS command injection, we will not receive immediate output confirming that our execution succeeded. Let's discuss ways of confirming that our command ran successfully when the application doesn't return any output from our injected command. One way to do this is with a sleep command. We can tell the target web server to sleep for an interval of time, say 5 seconds. And if we notice that after 5 seconds, the regular page content renders, then we have successfully identified that something is happening, and a blind command injection could be taking place. This means that any chained or extended commands work, even though there is no output. Let's try out a blind command injection vulnerability in our sandbox application by attempting to run the id command. Submitting our request in the browser, returns the following page. The page web content displays that the host is up. However, it would seem that there is no output from our id command. We're not sure if it even ran. Let's determine if this is a blind injection vector. To set a benchmark, we'll use the time command to measure how long our curl request takes against a server we know is down. According to the output, this took 10.12 seconds. This time may vary between virtual environments. Next, let's inject a 20-second sleep command to attempt to pause the request's execution. If the request pauses, we may have a blind injection vector. This time, the request took 30 seconds. Clearly, the sleep command ran. Very nice. We've discovered a blind command injection vector. In the next learning unit, we'll delve deeper into enumeration and exploitation of command injection by exploring capabilities, retrieving shells, conducting file transfers, and even writing our own web shell. Enumerating command injection capabilities. We've discovered command injection in our sandbox. Next, we need to discover what capabilities are at our disposal. Before we get down to receiving a shell or making noise from a network perspective, we should consider enumerating the target machine with our command injection. In our case, we'll use netcat in our command injection sandbox for file transfer and a shell on the target machine. File transfer is a crucial stage in payload delivery, especially after confirmation that we've received code execution on a victim machine. The thought process behind this is that we should always be aware of what our privileges and capabilities are on the target before throwing a bunch of potential weaponized code at it. For now, however, we can make a few simple checks fairly quickly to gain a good understanding of what we're permitted to do and what context we're permitted to do it in. We'll make explicit checks on the target machine for binaries such as the following. These are standard capability checks on a Linux-based target. Similar utilities exist on Windows. This is a very condensed list. Bear in mind that other utilities could assist with later stages, such as privilege escalation. Let's create a word list and search for Linux-based utilities with wfuzz. We'll also add woot woot as a baseline for a non-existent file. We'll now load our word list into wfuzz, excluding 404 response codes with --HC404. Our woot woot response had a size of 492 bytes. Some of the other responses were nearly identical in size, so we can assume that they also don't exist on the system. We'll give ourselves a slight buffer and assume that any response size greater than 495 bytes represents a binary that exists on the machine. By following this method of automating our checks for capabilities, we arrive at the following list. Now that we have a list of binaries, we can use them with any follow-up commands. In the next sections, we'll perform some file transfers and also establish stable reverse shells on our target. We'll also introduce a series of commonly used payloads, which are compact, lightweight, and practical for receiving a reverse shell. These shells are often referred to as one-liners. Obtaining a shell, netcat. Obtaining a reverse shell with netcat is fairly straightforward. On our attacking Kali Linux VM, we'll establish a netcat listener. Once we've established the listener, we'll use our command injection capability present in the Node.js CI Sandbox VM to gain a reverse shell with netcat. First, let's stand up a listener on port 9090. Next, we'll use command injection on the Node.js endpoint to execute the ID command and verify our privilege on the target machine. We'll use a single pipe operator to perform command injection on the ping command being executed by Node.js. Since Node.js seems to be running as root, we should receive a root shell. Let's try to get a shell. We'll use the -e option to execute bin bash, which will provide us with a prompt from the target. After loading this endpoint, we should get a shell on our listener. We do, and we discover that it is, in fact, a root shell. In the next section, we'll try a reverse shell with Python. Obtaining a shell in Python. Python is a very popular scripting language which is found on almost all Linux systems. This makes it a popular choice for penetration testers. Let's take the following one-liner and break it apart to explain how it works. This one-liner contains the following code. To create and send a reverse shell with Python, we'll create a socket, then connect it to our listener, duplicate the input, output, and error descriptors, and call bin sh with subprocess. To test this out, we'll first establish a netcat listener on port 9090. Next, we'll send our full request with the included Python payload. Once we've sent the request to the target web server, the output shows that we have received a reverse shell as www.data. However, since we don't have a valid TTY, this shell does not have job control, and that's not ideal. Next, we'll continue our hands-on work with command injection via poor input sanitization with Node.js. Obtaining a shell, Node.js. We already know that our target web application is running Node.js. In this section, we'll discuss how we can use Node.js itself to provide us with a shell. We'll use a chained attack approach to accomplish this. Like Python, Node.js also uses modules. Our initial command injection will place a malicious file in a world-writable directory that calls Node.js's child process and exec functions. The exec statement will contain the netcat reverse shell payload. Second, we'll need to execute the Node.js code. To do this, we'll chain the payload with a semicolon and execute node with a value of /var/temp/offset.js. Let's build our payload and prepare to submit it in our browser. To avoid any input sanitization, we'll first URL encode the payload. With our payload URL encoded, let's establish a netcat listener on port 9090. With our listener ready, let's visit the endpoint. Submit the payload, and switch back to our listener. Excellent. We received a reverse shell from our Node.js one-liner. In the next section, we'll explore various PHP one-liner examples. Obtaining a shell with PHP. Next, let's explore a variety of PHP one-liner reverse shell payloads. We'll analyze and contrast these approaches, beginning with the first half of each payload. This code instructs PHP to run the command within quotes. Specifically, we'll establish a TCP socket to our attacking machine's IP and listening port number. Next, we present a few variations. The first example uses exec, which is a function that executes a program. Next, we have shell exec, which executes a command via a shell and returns the output as a string. Next is system, which executes a command similar to exec and displays the output. Next, pass-through executes an external program and displays the output as raw. popen executes a command via opening a process file pointer and specifying a mode, such as R for reading. We can also use the PHP info function, which, if enabled, lists configuration information about the PHP installation. Let's try this against our sandbox. The first item to note in the output is disable functions. Since this is a sandbox, there are no disabled PHP functions. We should also note the document root. This helps an attacker plant malicious files, discover exploitation paths, discover writable directories, and much more. If we cannot access PHP info directly, we could use command injection to run PHP info ourselves. This could help us troubleshoot a variety of injection issues against a target. Let's test out these payloads. As usual, we'll begin by starting a Netcat listener on port 9090. Next, we'll use the PHP system function to execute a bash reverse shell. This is our complete endpoint, including the command injection with a semicolon character followed by our PHP reverse shell payload. After a bit of URL encoding and escaping inside double quote characters, we end up with the following complete endpoint and payload. After sending the request, our Netcat listener caught a shell as www data. Very nice. We'll continue our discussion of payloads in the next section as we present a Perl-based reverse shell. Obtaining a shell in Perl. The final language we'll discuss is Perl. To begin, here is a Perl reverse shell one-liner. Let's examine the Perl code within quotes. Similar to the Python example, we've imported the Perl socket module for our TCP connection. Next, we'll set up variables for our IP and port and pass these into a socket call. Note that we're creating a TCP connection-based socket by setting the sock stream constant. Lastly, we'll initialize the TCP connection with the connect function and open channels for standard input, standard output, and standard error. As expected, the final line calls bin.sh. This is our URL encoded payload. Before we run it, let's start our netcat listener. After submitting the request, our netcat listener catches a root shell on port 9090, since our Node.js instance is configured to run as UID 0, or root. In the next section, we'll change our focus from reverse shells and discuss file transfer capabilities. This will allow us to use our own tools instead of those installed on the system. File transfer. In this section, we'll assume that we're unable to run any kind of system shell from the target system's command line. This will emulate a real-world scenario in which the target machine has been somewhat hardened in a way that would prevent our previous approaches. Our goal will be to instruct the target to download a binary that we can run to send a shell to our netcat listener. For simplicity, since the target is running the same operating system as our attack machine, we'll instruct it to download a copy of netcat from our Kali VM. First, we need to determine how we will download the file. To do this, we must determine which file transfer binaries exist on the target system. Once we find a binary capable of downloading a file, we can set up a compatible server to serve the binary from our Kali VM. We could use a word list like the one presented earlier or test for binaries one at a time. For example, let's use which to test for the wget command with this simple command injection against the target. Good, we have access to wget. We can use this to download the netcat binary from our attack machine. If we hadn't found any binaries that could assist with file transfer, we could use commands like echo, which we'll demonstrate in the next section. Let's set up a web server on our attack machine that wget can interact with to download the binary. The netcat binary is located in the bin directory. Let's copy it to our local web root with the cp command. Next, let's start Apache 2. With an Apache server in place, we could inject several commands to download netcat, make it executable, and then run it to send ourselves a shell. However, we'll try to do this with one command. Let's build our payload. First, we'll use wget to retrieve NC from our Apache 2 web server and save it locally with -O to var temp nc. Next, we'll make it executable for all users with change mode 755. Finally, we'll execute netcat. We'll disable DNS resolution with -n, increase verbosity with -v, connect to our netcat listener, which will be on port 9090, and execute bash when we connect. Next, we'll normalize the payload. Before we send the request, let's set up our netcat listener on our Kali VM. As expected, we'll notice that we have caught a shell as www.data. We downloaded the binary, changed the permissions, successfully executed it with a one-line command injection, and we have our shell. Excellent. In the next section, we'll write our own web shell. Writing a web shell. If we don't have access to unique binaries but know the web technology in use, such as PHP in this example, we can write our own backdoor to achieve a shell with a web shell. We have command injection on our sandbox, so let's use echo to write a one-liner web shell in the target's web root. The first piece of information we need is our working directory, the document root. We can find this with the pwd command. Let's submit this URL and examine the output. Our output is displayed under the ping results. The document root is var www html php. Let's try to create our web shell in the web root of the target. We'll inject the following statement to create our web shell. It uses PHP's pass-through to execute our commands and display the results in the browser. Here's our full endpoint. After sending the request, we'll run ls by browsing to the following page to validate that our web shell was successfully created. We now have the ability to execute system-level commands via the cmd parameter and have listed out the contents of our web root. Before concluding this section, let's examine a significant limitation of our web shell. Let's try to change directories and list out the contents by chaining cd into ls-lsa with our cmd parameter. The output shows the directory listing of the root file system. At first glance, it would seem that we were able to successfully change directories. However, if we list the contents of the current directory, we'll notice our web shell's limitation. It might seem that we've returned to our web root, but the truth is we never left web root in the first place. This is because we are only calling pass-through to execute a command on our behalf. We don't have access to a typical shell's environment variables to let the Linux kernel know which directory we're currently in. Now that we know how to write our own web shell, where to write it, and the importance of using that foothold for a reverse shell, we'll move on in our case study and examine OpenNetAdmin, an IP network manager. Discovery and assessment. We'll begin this black box assessment by browsing to the home page for the OpenNetAdmin application. The application lists our privilege level in the top right of the page. We currently have limited guest privileges. To address this, we'll log in with the default credentials of admin as both the username and the password. Now that we're logged in as admin, we have full access to the web application and all of its features. We'll now begin to analyze the application. Along the way, we'll take note of any interesting parameters, functionality, or inputs. Let's explore the app and search for existing networks. Clicking Search will display services and associated hosts. This is the core functionality of the application and an excellent place to start. The Nmap scan entry in the list implies that OpenNetAdmin supports Nmap functionality. After clicking View Report, we note that OpenNetAdmin contains several alarming features, including Nmap and ping. We've used ping previously in this topic, so let's continue in that direction by clicking Ping to verify. We are then presented with a ping results window. Based on this output, it seems the application is running the system's ping command. Let's explore this further to determine if we have a vector for command injection. Exploitation. Let's further explore the ping function, determine if a vulnerability exists, and if so, figure out how to exploit it. Since it doesn't appear we can manipulate GET parameters from the browser's URL bar, let's open Burp Suite and enable the Intercept feature located under the Proxy tab. Next, we'll click on Ping to verify in OpenNet Admin and further analyze what is happening. Burp immediately intercepted the request. Unfortunately, it doesn't appear that any parameters are passed to ping, so we don't have an obvious attack vector in this initial request. However, let's continue to forward the initial request and analyze that data. This may reveal post data we can manipulate, such as an IP or other destination argument. This reveals an IP parameter that is sent to ping. This is dangerous territory for OpenNet Admin. If we are able to use any command separators, logical operators, or inline execution statements and receive expected terminal output, we will have confirmed command injection. Let's right-click in the request and select Send to Repeater so we can modify the request to test various manipulations in an attempt to extend the command's functionality. We'll work within the IP parameter. Let's inject ;ID as a simple command injection test. Here's the full set of post data and arguments of our attempted command injection. Let's update the request. If everything goes according to plan, when we click Send, we could have command injection on the target machine. Our ID command executed. We have validated a command injection vector and can perform remote code execution. Excellent. This machine is now completely compromised.
Interacting with the vulnerable server. We can use an SSRF vulnerability to interact with the loopback interface of the vulnerable server. If we can control the URL and submit localhost, the vulnerable application will send a request to its own server. Such a request can access ports that are not externally accessible. Let's review an example of this on our Kali host with Burp Suite running. By default, Burp Suite will start a listener on port 8080 of the loopback interface. We can verify this by running netstat with -L to list all listening sockets, -N to disable name resolution on the sockets, and -T to limit the results to TCP sockets. The results verify that Burp Suite is listening on the loopback interface. Let's try using curl to access port 8080 on the loopback interface. We were able to access the web page running on port 8080 through the loopback interface. Next, let's try accessing it with our Kali VM's actual IP address. Since Burp Suite is listening on the loopback interface and we tried to access it with our VM's external IP address, our VM refused the connection. If we were running a web application vulnerable to SSRF on our Kali VM, an attacker could use the vulnerability to access the Burp Suite page through the loopback interface. This example used an HTTP service, but suppose we had an SSH service or a database listening on the loopback interface. The SSRF vulnerability would be able to interact with those services as well. Even if the internal services don't return valid HTML content, we can still perform basic service enumeration through SSRF by checking for common TCP ports. Depending on the user agent generating the forged request, we might be able to make non-HTTP calls. We will discuss these attacks in a later learning unit. Discovering SSRF vulnerabilities. SSRF vulnerabilities can be present in applications that allow users to upload files from a link rather than submitting a file directly. If we discover this kind of upload functionality or find suggestive parameters like URL, URI, or link, we should test the application for SSRF. In some cases, the vulnerable application will request the resource we specify and then display the results of the request. This is known as a basic SSRF, and it allows us to easily retrieve data that we might not have direct access to. Let's demonstrate this with the SSRF Sandbox application. We'll access the Preview Link function on the SSRF Sandbox. We can use this application to generate server-side requests with curl, wget, or Python's requests library. Let's test this app by making a request to megacorp1.com. We'll leave utility set to requests library and click submit. Note that the SSRF Sandbox loaded the index page from megacorp1.com. The SSRF was successful, and although the HTML did not render, we have access to the requested page's raw HTML source. This is a fairly simple example. However, some applications accept a URL or link and will verify it exists with a GET or HEAD request. This is known as blind SSRF since we do not have direct access to the request's content. This is more difficult to exploit, but we can still leverage the information the application does return. Let's demonstrate this with the Verify Link function, which we can access by clicking Verify Link on the top left-hand side of the application. Let's send a request to megacorp1.com, leave utility set to requests library, and click submit. The page displays URL verified, but we have no other indication of what the application did. Since we seem to control the full URL, let's send a request to a system we control, our Kali VM. Calling home to Kali. If we can force an application to connect to a server we control during an SSRF attack, we can gain greater insight into the application and the attack itself. Even if the application returns the results of the forged request, having the application request a page from our server can leak important information about the application through the user agent header. In a real-world situation, we would need to make sure the victim machine could route to our vulnerable server. However, we can try this out in our lab environment with our Kali VM. First, let's make sure we have Apache running. Next, we'll submit our Kali VM's IP address in the URL field. Let's type our IP address, including the HTTP protocol prefix, appended with Hello SSRF World, and click Submit. The application might return a 404 status, but let's check our Apache log files with the tail command. Excellent! The Sandbox application made a GET request to our Kali VM. We've verified the SSRF vulnerability and also identified that the vulnerable application was written in Python. Retrieving data. What we can do with an SSRF vulnerability depends on how the application sends the forged request. For example, the user agent sending the request might not follow redirects. If the application always sends GET requests, we may be limited to retrieving other HTML pages or basic service enumeration. Let's walk through an example of how to retrieve another page in the SSRF sandbox. First, notice that an attempt to access the status page results in an error message. The error message states, "Remote access denied." Perhaps there are IP restrictions in place that prevent us from accessing the page. Let's try using the SSRF vulnerability to access it. Remember, when we exploit an SSRF vulnerability, the application sends the request on our behalf. If the application checks IP addresses, the request would contain the IP address of the server itself. We'll click on Preview Link, enter localhost status in the URL field, and click Submit. Our SSRF exploit was successful, and we were able to access the contents of the status page by forcing the application server to request it on our behalf. Although we can access the status page, the application we are sending the forged request to may limit our capability. For example, many applications use POST or PUT requests for actions that change state. Those same requests might also require authentication in the form of a session cookie or authorization header. If we can only control the URL field, we may be limited to the default request method generated by the application. Later in this learning unit, we will cover some ways to bypass these restrictions based on alternative URL schemes. Alternative URL schemes. Depending on the user agent that generates the forged request, we might be able to use protocols other than HTTP and HTTPS by submitting URLs with different scheme values. A scheme is the first part of a URL that normally precedes a colon. Each scheme has a corresponding protocol. Sometimes protocol and scheme are used interchangeably. In the previous example, the scheme is HTTP, which corresponds to the Hypertext Transfer Protocol. The terms seem interchangeable when used to reference HTTP, but there are several different versions of the protocol that all use the same URL scheme. Generally, the user agent will specify the HTTP version as part of a request. When we encounter an SSRF vulnerability, We should also test which protocols and schemes the application will send. Some user agents will support the file scheme, which allows us to reference files on the vulnerable server. A valid file URI requires a host and a path after the scheme and colon. However, we can also omit the host value by using 1 / to indicate there is no host name, or using 3 / to indicate an empty host name. Most operating systems treat these two options the same, but some might handle them differently. We can find an example of a file URI in the default homepage of Firefox in Kali. In this example, Firefox rendered a file from our local file system with a URI that starts with file, and 3 /. We can verify this file exists on our local system using the head command followed by the path. Since we opened the file URI in our browser on our Kali VM, our browser accessed the local file. If we exploit an SSRF with a file URI and the application or command that sends the forged request supports the file scheme, the vulnerable application may access and render a file from its own server. Let's try an example of this in the SSRF sandbox. Let's enter file etc password in the URL field, leave requests library selected in the utility field, and click submit. The application responded with a generic error message. Without more detail, we must guess what went wrong. Perhaps the application does not support the file scheme, or the server is not a Linux server, which resulted in an invalid file path. However, if we submit a Windows-based file path, we receive the same error. Let's try a different utility. We'll change the URL field back to file etc password, change the utility field to curl, and click submit. Excellent. Curl supports the file scheme, and we were able to retrieve the contents of etc password from the remote system. As we've discovered, the Python requests library does not support the file scheme. As this example demonstrates, we need to understand what user agent generates the forged request to determine if we can use alternative URL schemes and increase the severity of the attack. Some user agents support the Gopher protocol, which we can use to bypass some of the restrictions of a traditional SSRF vulnerability. Gopher dates to the start of the World Wide Web, but its usage has declined since then. Curl still supports the Gopher protocol and allows new line characters in URLs. When we use curl to send a request using the Gopher protocol, we can use new lines to inject headers in the request. In fact, we can use Gopher URLs to create valid requests in several different protocols, including HTTP. Let's try using curl on our Kali VM to familiarize ourselves with Gopher. We'll start a Netcat listener on port 9000. Now that we have our listener running, we'll open a new terminal tab and call our listener using curl and the Gopher URL scheme. the terminal window will pause while it waits for a response from the Netcat listener. Let's switch tabs and check the output on the listener. Our listener received the request, but the first character of the URL path is missing. Our listener will keep the Gopher connection open, so we'll need to stop it with Control-C. Let's try sending an HTTP request in the path of our Gopher URL. We'll need to remember that the first character of the path gets truncated. Before we demonstrate this, consider this standard curl GET request. Let's try to recreate the first line of a normal HTTP GET request. We'll use an underscore as the first character of the path since it gets truncated. We'll need to URL encode spaces as %20 to create a valid URL. Our resulting value is as follows. Let's restart our listener and then submit our payload to it using curl. Let's check our Netcat listener. The first line of our request now mimics a normal HTTP request. We may need to include additional headers depending on the server processing such a request and how strictly the server validates it. For example, we may need to include a line feed character, %0a, and a host header. Since we are including the GET request as part of the path, we can easily change it to a different HTTP method. Let's try using the Gopher protocol on the SSRF sandbox. Let's switch to Burp Suite's embedded Chromium browser. Next, in the Preview Link page, confirm curl is selected in the Utility field and enter the following payload in the URL field. We need to include port 80 in our URL because the Gopher service normally runs on port 70. Let's click Submit. Excellent! Our Gopher request was interpreted as an HTTP request by the server, and we were able to retrieve the results of the status page. However, we still sent a GET request, which we were already able to do. Let's try changing our payload to send a POST request by replacing GET with POST. We'll enter the following payload in the URL field and click Submit. The application responded with an HTTP 405 message indicating the server does not allow POST requests to the status page. Even though we received an error message, this means the server interpreted our Gopher payload as a POST request. We are missing one important detail. If we tried to replicate this attack using curl on our Kali VM, we would encounter a problem. The application does not receive the exact payload we've entered in our browser. In fact, our browser URL encodes the %signs, creating double encoded values. We can verify this by checking our requests in the HTTP History tab in Burp Suite. Our browser URL encoded all non-alphanumeric characters. In the case of the %sign, this resulted in each space character being double URL encoded as %2520. The application essentially processes our request twice. The application first processes it as the request to preview. This request triggers the SSRF attack, which sends another request, in this case the GET request. Since the payload values are double encoded, The application does not fully decode the payload until it processes the second request. If we were to replicate this attack from curl or in the repeater tool, we would need to double encode any non-alphanumeric characters as well.